Anyone who's ever had to pack for a trip has probably known the frustration of trying to cram almost a suitcase worth of stuff into a backpack. I mean, sure, we could suck it up and leave a few items behind, or haul around our bulky luggage with us if they're so important. But other than that, it was pretty much a perfect analogy for why data compression became so important to reduce storage requirements and to improve transfer speeds over standard connections. Obviously, data can't be rolled in quite the same manner as slightly pre-worn laundry, so coding engineers devise algorithms capable of breaking down longer strings of data into shorter ones, then reassembling them later using what they've retained. An easy way to describe this would be like breaking down the equation 2 times 2 times 2 times 2 times 2 into 2 to the 5th power, which is much faster to write and simpler to articulate. While it is possible to write a command string which describes an exponential function, it usually isn't much of a space saver, so maybe a better way to demonstrate how a compression algorithm works is to use something like a string of X's and O's, or zeros and ones if you're catching the similarities here. Let's say we have a string of 8 digits, which is spelled out as XXXOOXXX. Now, an algorithm may look at this and decide that every time it comes across a new digit, it will replicate it and then note how many times it's been repeated. This would cause our string to transform into the smaller X302X3. While this did reduce overall size, it only managed to do so by 25%, which isn't exactly going to allow us to cram our drives full or transfer large files over the internet more efficiently. That's where more specifically designed algorithms will come in to strip the code to its most basic form, instead simply adding all the X's together by treating each as a value of 1, then listing all the O's followed with a digit count as before. Then we end up with a string that would look like 3023, which we can now see is half the size of the original code. Now obviously this example is rudimentary at best, but it gives an idea of how mathematicians are able to achieve and then further improve upon this feat as time goes on. Now, this example would be known as lossless compression. All of the original data remains intact and is a requirement for programs or documents. But if you're willing to give up some detail in the original file, lossy compression algorithms can be used for media files like music and movies, as long as you understand that the tighter you cram it, the lower the playback quality you'll experience, which you can actually learn a little bit more about here in our video specifically about video compression.